Our planet, Earth, is incredibly old. Imagine a timeline stretching back 4.6 billion years. That's older than the oldest mountains, older than the oceans, older even than the sun itself. How do we know this? How can we possibly grasp such immense stretches of time? The story begins with the Big Bang, the event that birthed our universe. From a hot, dense state, space expanded, cooled, and elementary particles formed. Gravity drew these particles together, creating the first stars and galaxies. Our sun, a latecomer, formed from the remnants of previous stellar explosions, inheriting a swirling disk of dust and gas. Within this disk, tiny particles collided and stuck together. Over millions of years, these clumps grew, their gravity pulling in more material. This is how our Earth was born, a fiery ball of molten rock constantly bombarded by asteroids and comets in the young solar system. As Earth cooled, its molten surface solidified into a crust. Volcanoes erupted, spewing gases that formed our early atmosphere. Water vapor condensed and fell as rain, filling the first oceans. These were the chaotic early days of our planet, a time of intense geological upheaval. Unraveling Earth's epic history requires ingenious methods. One such method, radiometric dating, acts like a cosmic clock embedded within rocks. It relies on the predictable decay of radioactive isotopes, variants of elements with different numbers of neutrons. Uranium-lead dating, for example, is used to date some of the oldest rocks on Earth. Uranium, a radioactive element, slowly decays into lead at a known rate. By measuring the ratio of uranium to lead in a rock sample, scientists can calculate its age. Other radiometric dating techniques use different isotope pairs, each suitable for different age ranges. Carbon-14 dating, for instance, helps determine the age of organic materials up to tens of thousands of years old. This method is particularly useful for archaeology and paleontology. These methods, refined over decades, provide a powerful toolkit for scientists to piece together Earth's history. They reveal a planet that has undergone dramatic transformations over billions of years. The early Earth was a harsh and unforgiving place. Volcanic eruptions were commonplace, and the atmosphere was toxic to life as we know it. Yet, remarkably, life emerged from this primordial soup. The first life forms were simple, single-celled organisms, likely appearing around 3.5 billion years ago. These early microbes, called prokaryotes, lived in the oceans, finding energy in chemical compounds spewing from hydrothermal vents. These organisms, though primitive, possess the remarkable ability to replicate themselves, passing on genetic information. This marked the beginning of life's long evolutionary journey, a journey that would eventually lead to all the plants and animals we see today. The emergence of photosynthesis, around 3 billion years ago, was a pivotal moment. Photosynthetic organisms like cyanobacteria evolved the ability to harness sunlight to create energy, releasing oxygen as a byproduct. This gradually transformed Earth's atmosphere, paving the way for oxygen-breathing life to evolve. The increase in atmospheric oxygen had profound consequences for life on Earth. Oxygen is a highly reactive element, and its presence in the atmosphere allowed for the evolution of more efficient forms of respiration. This, in turn, provided organisms with more energy, enabling the development of larger, more complex cells called eukaryotes. Eukaryotic cells, with their membrane-bound organelles, are the building blocks of all multicellular life, from fungi and plants to animals and humans. Around 600 million years ago, life on Earth underwent a dramatic burst of diversification known as the Cambrian explosion. During this relatively short period, a dazzling array of new life forms evolved, including the first animals with skeletons and hard shells. The fossil record from the Cambrian period reveals an astonishing variety of bizarre and wonderful creatures, showcasing evolution's creativity. This period marked a turning point in Earth's history, setting the stage for the evolution of all subsequent life forms. While life was evolving and diversifying, Earth's continents were also on the move. Driven by the slow churn of the mantle, the layer beneath Earth's crust, continents have drifted across the globe, colliding and breaking apart over eons. This process, known as plate tectonics, has shaped Earth's surface, creating mountain ranges, ocean basins, and volcanic hotspots. It has also influenced Earth's climate by altering ocean currents and atmospheric circulation patterns. Climate change, driven by both geological and astronomical factors, has been a constant throughout Earth's history. Periods of intense heat have been followed by ice ages, each leaving their mark on the planet's life forms. Understanding these past climate changes is crucial for predicting future trends and mitigating the impact of human-induced climate change, one of the most pressing challenges facing humanity today. Our journey through Earth's history reveals a planet that is both ancient and ever-changing. From the fiery chaos of its birth to the emergence of life and the evolution of complex ecosystems, Earth's story is one of constant transformation. The techniques we use to unravel this history, like radiometric dating, provide a powerful lens through which we can view the deep past. They remind us of the immense timescales involved and the profound changes that have shaped our planet. Understanding Earth's timeline is not just an academic exercise, it provides crucial context for our place in the universe and the impact we are having on our planet. It allows us to appreciate the interconnectedness of life, the delicate balance of Earth's systems, and the importance of preserving biodiversity for future generations. As we continue to explore our planet, from the highest mountains to the deepest oceans, we are constantly uncovering new chapters in Earth's epic story. This story, still unfolding, reminds us that we are part of something much grander than ourselves, a cosmic narrative billions of years in the making. Don't forget to like, subscribe, and hit the bell icon so you never miss an episode. Share your thoughts in the comments below. How do you feel knowing the Earth is 4.6 billion years old? See you next time on 5 Minute Geology.